Every plane, missile, or object that moves through Earth's atmosphere is first tested as an experimental aerodynamic model built to scale. Simulated environments, essential for such testing, permit aerodynamic theories to be proven before full-scale prototype production begins. General Dynamics facilities in San Diego, California, include 3 wind tunnels and a complete array of supporting workshops and data-gathering equipment. Available to any organization requiring model verification or design refinement, these tunnels can meet your wind speed requirements, giving your model wind environments, Mach 0 to Mach 12. Subsonic at the low-speed wind tunnel. Transonic and supersonic at the high-speed wind tunnel. And hypersonic at the hypersonic wind tunnel. How this wide spectrum of wind velocities is used is determined by the flight requirements for each specific model design. For airspeeds up to 300 miles per hour, the low-speed wind tunnel, a closed-return, atmospheric-type tunnel where the airflow travels a 350-foot-long rectangular path. There are 2 test sections. One produces airspeeds up to 70 miles per hour. It is 20 feet wide, 14 feet long, 16 feet high, and is intended primarily for models with high-energy lift systems. A smaller test section farther upstream furnishes higher air velocities. It is 12 feet wide, 15 feet long, and 8 feet high. A variety of support systems assures selection of the one best suited to a particular model or test. Ample windows and lighting systems provide excellent visibility for cameras and observers. During tests, force data are recorded using either internal strain gauge balances installed in the model or the tunnel's external balance system directly beneath the test section. Mounted on a 165,000-pound inertia block, the system resolves air loads imposed on the model, measures them as changes in hydraulic pressure, and transmits the measurements to the control room. Power for the low-speed wind tunnel comes from variable frequency electrical equipment in an adjacent building. Models with motors and propellers get their power from 2 independent systems. A larger electrical system powers the 2,250 horsepower synchronous motor which drives the tunnel's propeller. This 6-bladed fan, 20 feet in diameter, creates the desired airflow. 5 steel support struts remove the rotational effect from the airstream, enabling the model to react as though it were moving through the air. Tests are directed from a control room adjoining the test section. Keyman, the customer's test engineer. His job, confirm model configuration, test parameters, and data to be recorded for each run. After starting the tunnel, the operator sets the airspeed and model attitude. Preset schedules can be reached either manually or automatically. When tunnel conditions have stabilized, he records the data. A pressure scan-a-valve system greatly increases the quantity of obtainable information. Data can be plotted online, manually, and through XY plotters for a pictorial presentation of results while tests are still in progress. Other online equipment, like oscilloscopes or oscillographs, is also available. Light banks display all data which are recorded, both in tabular form for online inspection and analysis, and on punched cards for subsequent data reduction. Up to 50 channels of inputs can be recorded, including appropriate model and test parameters, and data from strain gauge balances or pressure transducers. Following each test run, the punched cards go to the data processing room. Here, a computer system reduces the data according to customer specifications. A staff of programmers converts data reduction equations to computer operations. Within minutes, the final data output is available in both plotted and tabulated form. The objective? Provide the customer with the essentials for an efficient test program. A wide range of special test equipment and knowledgeable personnel are the hallmark of the General Dynamics wind tunnels. At the low-speed wind tunnel, for example, the variety of flow visualizations includes thread tufts, tuft grids, French chalk, oil, and water vapor. Also available, ground simulation facilities for takeoff and landing configurations, and facilities for two-dimensional testing, dynamic ejection testing, flutter model testing, and powered propeller-driven model testing. A high-pressure auxiliary air system provides clean, dry air to the hazardous test area. Model motors, high-pressure air systems, and other special installations can be thoroughly checked for safety before tunnel testing begins. Setup, calibration, and checkout performed here increase tunnel efficiency. Available to both test sections and customized for each specific test, this high-pressure system permits jet engine simulation and the simulation of boundary layer control devices. It delivers air at pressures up to 500 pounds per square inch, at flow rates up to 22 pounds per second. An 8-inch underground pipeline delivers this air to the low-speed wind tunnel from compressors in the high-speed wind tunnel about a mile away. Here, in addition to the compressors, there are 6 compressed air storage tanks. The high-speed tunnel provides this air to all 3 facilities. W.T. McCarthy is manager of the wind tunnels. His offices are in this complex, where testing involves wind velocities from 1/2 to 5 times the speed of sound. Air, compressed to 600 pounds per square inch, blows down this open-ended wind tunnel for 20 to 60 seconds, depending on specific test requirements. A quick-acting valve controls the flow of air, which is then exhausted from the end of the giant tube. Within 20 to 50 minutes of each run, the storage tanks are again up to their maximum pressure of 600 psi. An 8,000 horsepower engine drives the compressors, which are cooled with San Diego Bay water. To keep tunnel downtime at a minimum, most of the model mounting is done outside the test area on a setup cart. Then, when the facility is ready, the entire assembly can easily be transferred to its test section, virtually ready for the first run. During conventional testing, a model cart supports the test specimen in either the transonic or the supersonic test section. Each section is 4 feet wide and 4 feet high. Models tested in the high-speed wind tunnel normally measure between 3 and 4.5 feet in length. This is true even when using the 6-foot-long special test section designed for complex wall-mounted specimens. Here, proximity plates reduce the high starting airflow loads which are intolerable to some supersonic models. Tunnel closing occurs only after model installation has been properly completed. A last-minute check of the 250-foot-long tunnel verifies its readiness for the release of air at the desired Mach number. A quick-acting rotovalve controls the airflow during blowdown. Complete access to the model within minutes after each run permits changes as the testing sequence progresses. The control room houses the data acquisition system and the consoles that trigger all testing functions. The General Dynamics team always works closely with the customer. The operations crew chief handles all major controls, conveniently located on a single console, while the test conductor, using the vast amount of information at his disposal, guides progress of the testing sequence. Closed-circuit television monitors show the model during blowdown. TV coverage can be recorded on videotape and played back immediately for analysis, or sent to the customer's home office for engineering review and evaluation. A single test run provides a complete spectrum of data, such as the pitch of a model through an entire angle of attack range, an entire yaw maneuver, a complete roll, or several different throttle settings of a nozzle inlet. Mach numbers, Reynolds numbers, model configurations, and changes of this nature are usually made between runs. Shock waves can be observed using the Schlerin system. They can also be recorded on videotape or film. Currently, the data acquisition system records up to 200 channels of data at sampling rates up to 25,000 channels per second. There is an adjustable delay between data points. Data are transmitted directly to the data processing room for immediate reduction. As a customer, you determine how your data will be handled. A printout machine furnishes the corrected data minutes after the run. Several minutes later, a plotter produces the final computed corrected coefficients in graphic form. Prompt evaluation of the plots will permit your test conductor to adjust the test program, making best use of tunnel time. The captive trajectory system permits wind tunnel analysis of the trajectories of missiles or other stores released by aircraft. An analog computer, using force data measurements from the model in conjunction with other data, computes the resulting trajectory. The trajectory is then simulated with a 6 degree of freedom support. With the parent aircraft model suspended from the ceiling, and the missile suspended independently by the 6 degree of freedom support. The computer-controlled system simulates the trajectory of the projectile during separation. Inertia and propulsion characteristics of the missile itself can also be simulated. Such studies afford both the aircraft and missile manufacturer a dynamic tool with which to analyze the complex problem of missile and store separation. Drop testing, another form of trajectory testing, involves the physical action of dropping stores during blowdowns. Two high-speed precision color cameras simultaneously record the trajectory, one from the side, the other from below. Other cameras can be added, providing additional fields of view from these basic angles. Nearby processing facilities provide color motion pictures within hours, or black and white footage within minutes. Films of store separation from the aircraft can be read on a telereadex. These data, when transferred to punched cards, are fed to a computer where the three-dimensional trajectory is determined, listed, and plotted. In addition to accommodating a multitude of test requirements, this wind facility also furnishes air volume and pressures for the hypersonic wind tunnel. A closed-circuit television system provides model viewing either directly or with a Schlieren system. A nozzle with interchangeable throats enables this intermittent-type facility to produce wind speeds of Mach 8, 10, and 12. Such wind speeds at the model test point require a two-stage ejector system downstream of the test region. These ejectors create a low air pressure tunnel area aft of the test section, preventing air blockage and sustaining the flow. Air for the nozzle comes from compressors of the neighboring facility on a continuous basis, while the supply tanks furnish air for the ejector system on a limited basis. A gas heater warms the nozzle air to temperatures of from 900 to 1100 degrees Fahrenheit, preventing moisture buildup in the test section. The chamber is about 8 feet high, 4 feet wide, and 6 feet long. A 4x6 rolling door provides access and is pneumatically locked when closed. The support injects the model into the flow after tunnel start and pitches the model during the run. Consoles in the blockhouse control all test functions. These include heater controls, pressure and temperature displays, valve status board, and safety interlocks for the tunnel. Auxiliary controls, such as model support and data take, are also located here. Immediately after the run, information from the readout system can be checked and delivered to the computer in the high-speed wind tunnel for final data computation. Whatever your wind tunnel needs may be, General Dynamics can meet them. Model design, construction, modification, or repair. Internal balance design and construction. Installation. Calibration. And all types of instrumentation. These wind tunnels will fill the needs of any organization seeking model design, refinement, or verification. Regardless of ultimate goals, experimental trips into the atmosphere can first take place within these facilities. General Dynamics offers you controlled wind environments, giving your model